Okay, so in lesson 7 on complex numbers, the main plan is to, by the end of the lesson, teach you how to find square roots, cube roots, fourth roots, fifth roots, however many roots you want of any complex number. I'm going to teach you to find the nth roots of any complex number. And that's the same as saying the solutions of z to the n equals that complex number. So the nth roots of a number alpha are the solutions of z to the n is alpha. In order to introduce this, we're going to do something which might seem a little bit strange. I am first of all going to show you how to find the nth roots of the number 1, the simplest number I can think of. And these are sometimes called the nth roots of unity. These are the solutions of z to the n is 1. Now, when we get to the point of working out nth roots of complex numbers, it's going to turn out that writing the complex number in exponential form, or polar form, so r e to the I theta or r cos theta plus I sine theta will be extremely useful. But I'm going to start looking at equations of this form. For small values of n is 2, 3, 4, and we'll see that there's a nice pattern you get in terms of the solutions of z to the n is 1. So the first thing it says, find the square roots of unity. This is the solutions of z squared is 1. So in absolutely straightforward maths, if z squared is 1, z is a plus or minus 1. And I'm going to show these on an Argand diagram. So 1 is 1 on the positive x-axis, minus 1 is 1 on the negative x-axis. There are two solutions, and there they are. It is quite easy to write these in exponential form. Now I'm going to leave number 1 as it is. Minus 1 is the complex number whose modulus is 1 and argument is pi. So therefore that's e to the power of pi I. That's minus 1. That's that complex number there. I've shown them on an Argand diagram, and the sum of the roots is obviously minus 1 plus 1, which is 0. Trivial. Okay. Let's see what happens next. So the first interesting case is I try to find the cube roots of unity, which are the solutions of z cubed equals 1. Now, there is an obvious solution, which is z is 1. And I'm going to find that, and I'm going to find the other solutions. I'm going to do this algebraically, but it's not that big a deal by turning this into a cubic equation. So this is the same as saying z cubed minus 1 is 0. If you stick in z is 1, you get 0. So p of 1 is 0. So therefore, that means z minus 1 is a factor. If you then use long division to work out the quadratic factor, or you can use inspection, the quadratic factor turns out to be z squared plus z plus 1. So this gives roots of z equals 1, and then that quadratic, if I solve that on my calculator, menu, solver, so it's polynomial of degree 2, so a is 1, b is 1, and c is 1. So that turns out to complex roots. So that one there, minus 1 plus root 3i over 2, and then the other one is minus 1 minus root 3i over 2. So I'm going to write down z is 1, and the other roots could be written as z is minus a half plus or minus root 3 over 2i. So z is 1 is kind of the obvious solution of the equation z cubed is 1. Minus 1 plus or minus root 3 over 2i, that's the less obvious solution. But can I just show you on an Argand diagram? So 1 is here, minus a half root 3i is here, minus a half minus root 3i is roughly here. Now it says, write these roots in exponential form. Well, 1 is, I'm just going to leave, is 1 is 1. The other ones, if I, on my calculator, type in minus a half, oops, exit menu. If I type in minus a half plus root 3 over 2, if I convert it into the standard form by pressing option complex, it's got a modulus of 1 and argument of 120. Surely I want to be in radians. So it's got a modulus 1 and an argument of 2 pi over 3. So therefore, it is in exponential form 1 times e to the power of 2 pi over 3i. And if we do the same for minus a half minus root 3 over 2 pi, change that to minus. I get it's got argument 1, sorry, modulus 1 and argument minus 2/3 pi, but minus 2/3 pi is equivalent to, because you add on 2 pi, you get the equivalent angle 4/3 pi. Therefore, that's what that is. There they are in exponential form. Here they are shown on an Argand diagram, and it's worth bearing in mind the following. They obviously form a triangle, but actually the following is true. That angle there is 60 degrees, so 120 degrees, 2 pi over 3. That angle there is 120, that angle there is 120. They form an equilateral triangle on an Argand diagram. So that's nice. Center is the origin. The complex number at 1 is one of the vertices, and the other vertices can be worked out geometrically. Shown on an Argand diagram, the sum of the roots is 1 plus minus a half plus root 3 over 2i plus minus a half minus root 3 over 2i. And that very conveniently adds up to easy. So there you go. Key points are the complex solutions of z cubed is 1. There are 3 complex solutions. One of them is 1. The others in exponential form are e to the 2 pi over 3i. That's because the angle at the center of the circle, 2 pi radians, has been split into 3. And then the next one is e to the 4 pi over 3i. They form an equilateral triangle in the Argand diagram, and the sum of the roots is equal to 0. Next one, let's find the solutions of z to the 4 is 1. So again, I'm going to do this algebraically, because I can do this quite easily without doing anything complicated. If you square root twice, if you square root once, you get z squared is plus or minus 1. And then if you square root those, well, if z squared is 1, you get z is plus or minus 1. If z squared is minus 1, you get z is plus or minus the square root of minus 1. So that is plus or minus I. So the solutions of z to the 4 is 1 are here. There they are, plus or minus 1, plus or minus I. So that is 1, minus 1, I, and minus I. So let's call them I and minus I. There you go. Okay. That's those complex numbers. If you write them in exponential form, well, the first one is 1. The next one's got an argument of pi over 2, e to the I, pi over 2. The next one's got an argument of pi, e to the I, pi. And the next one will have an argument of either minus pi over 2, but between 0 and 2 pi, that's going to 3 pi over 2, so e to the 3 pi I over 2. I've shown them on the Argand diagram. The sum of the roots, if you do 1, add minus 1, add I, add minus I, it just cancels out to give 0. And these form an equilateral, quadrilateral, which you would probably call a square. So they form a square on an Argand diagram. So there's some sort of pattern going on here between these example and this example. The solutions of z to the 4 equals 1, there are 4 of them. You start at the number 1 and then you rotate around the Argand diagram for an angle of 90 degrees. That's because the total angle is 360, which is 2 pi radians, and you're dividing it by 4, and you do that repeatedly to get the other roots. So, assuming this pattern continues, can we now have a go at this? Can we predict what the solutions of z to the 5 equals 1 would be? So I'm going to actually do these kind of in this order. I'm going to show them on an Argand diagram. I'm going to do the sum of the roots. The first thing you should predict is z to the 5 equals 1 will have 5 roots, and one of the roots will be the complex number 1. The other roots will be equally distributed around the Argand diagram. They will all have a modulus of 1, but their arguments will vary. they will form an equilateral pentagon around the Argand diagram. Next root here, that argument is going to be, well, the total angle at the center is 360 degrees, 2 pi radians. So that angle there is 2 pi over 5, because the angle at the center is split into 5 separate angles. So it's e to the power of 2 pi I over 5. Then the next one, you double the angle, e to the power of 4 pi I over 5. Then you get triple the angle, e to the power of 6 pi I over 5. And then finally, e to the power of 8 pi over 5. Those are the fifth roots of unity. Those are the complex solutions of the equation z to the 5 is 1, written in exponential form. If you wanted them in x plus yi form, you could convert them on your calculator. I've shown them on a diagram, and the sum of the roots, well, if you convert them into x plus yi form and add them together, they all cancel out to give 0. The reason really is they are equally distributed around 0 around the origin on an Argand diagram. Now, in general, the nth roots of unity means the solutions of z to the n is 1 can all be written down in this way. The first solution is going to be z equals 1. The second solution is going to have modulus 1 and argument 2 pi divided by n, or whatever n will be, which is e to the 2 pi I over n. Then you double that angle, e to the power of 4 pi I over n. Then you do that angle again, e to the power of 6 pi I over n, and you keep on going until you get 6 different complex numbers. Those 6 different complex numbers will be equally distributed on an Argand diagram. They will lie in a circle of radius 1. They will form a regular polygon of size n sides on an Argand diagram. And the formula booklet essentially says this. So this is equivalent to saying what is in this box. So the roots of z to the n is 1 are given by z is e to the 2 pi ki over n, where k can be 0. And if you sub in k is 0 into that formula, then the whole of the power is 0. So you just get z is 1. K is 1 to get e to the 2 pi I over n. K is 2 to get e to the 4 pi I over n, etc. You stop at whatever n minus 1 is to give n different numbers in total. And that, my friends, is stated on the formula sheet. So that's something you don't need to learn. You could use that to literally write down the solutions of z to the n equals 1. There will be n complex numbers. There is another way of referring to this, which is sometimes shown. So if you called the first non-trivial root omega, so omega is what you get when you replace k with 1 in this formula, then the roots of unity are as follows. The first one is 1 and the next one is omega. Then you double and triple the power and stuff. So it's omega squared, ... all the way up to omega to the power of n minus 1. And that gives you n different roots in total in terms of this thing omega. Each of these points are the corners, the vertices of a regular n-sided polygon, an n-gon, and the sum of these will always equal to 0. So I'm just going to have a go example of this and then stop. That's the first part of this lesson done. So find the 6th roots of unity, i.e. the solutions of z to the 6 equals 1. Well, I know that the solutions are going to be z is e to the 2 pi ki over 6, because n is 6, where n is equal to 0, 1, 2, ... all the way up to 5. That's what that formula gives you. N is 6, so the roots are given by that formula. So consequently, writing them down in exponential form, if you that's where k is equal to those values. N is 6, k varies from 0 up to 5. If you sub in k is 0, you will just get 1. If you sub in k is 1, you get e to the 2 pi I over 6, which is e to the pi I over 3. If you sub in k as 2, you get e to the 4 pi I over 6, which is e to the 2 pi I over 3. If you sub in k as 3, you get e to the 6 pi I over 6, which is just e to the pi I. If I write down k is equal to 4, I will get e to the power of, it will be 4 pi I over, So if k is what's 8, so it's 4 pi I over 3, yeah, because it's 8 pi over 6. And if you put in k is 5, you will get e to the power of 5 pi I over 3. I'll show you on an Argand diagram. So the first one is at 1, and then the other ones, they all lie on a circle. Let me draw my circle in. Center of the origin, radius 1, and they are equally distributed around there. So I draw a line up here, a line up here, a line down here, a line down here, a line down there. Those are these complex numbers. To write the roots in, I'll come back to that in just 1 second, the roots in Cartesian form. Show them on an Argand diagram. The sum of the roots is bound to be 0, it always is. To work out the roots on Cartesian form, you probably want to use your calculator to do this. So to work out, for example, e to the pi I over 3, the easiest way is, this is the complex number whose modulus is 1 and argument is pi over 3. So that's a half plus root 3 over 2i. And then if you change the argument to 2 pi over 3, you'll get minus a half plus root 3 over 2i. If you change the argument to 3 pi over 3, you just get minus 1. If you change the argument to 4 pi over 3, you will get minus a half plus root 3 over 2i. And finally, you'll get minus a half minus root 3 over 2i. Okay, folks, that's the first part of this lesson done. You should now be in a position where you can do exercise 7a.